So hello everyone, thank you for coming today, and thanks to the organizers of GopherCon for giving us the opportunity to talk about and share our work. You'll notice that the topic here has changed from Game of Clicks to recommendations that don't suck. The first title was conceived at the peak of the Game of Thrones hype cycle. Those of you who've seen the show may remember that very brief period. But because we live in the future and everything is interesting, for only 15 minutes, recommendations that don't suck is perhaps more direct and reflective of our aims. I want to flag something up front. This talk is about solving problems using Go, not solving Go problems. By this I mean I don't have any new or fundamental insights into concurrency or memory management. Rather, that this work is a kind of existence proof that developing more advanced enterprise-scale ML applications is indeed possible within the Go language ecosystem. The standard caveat also applies. I'm not here representing ABC editorial policy or making any kind of vendor or product endorsements. This is just a short talk on what I believe to be an important topic and a look into some of the work we're doing in this area. So let's get into it. So some structure first. I'm going to try and pack quite a bit into these 30 minutes, and I will, of course, be glossing over some things, particularly when it comes to sort of the background and theory of machine learning itself. Obviously, a big field with a lot of interesting theories sitting at the intersections of math, computer science, and physics. In short, this is a 30-minute talk that contains multiple 30-minute talks. I will try to zoom in on things that are really important and zoom out without losing sight of the overall story that I'm trying to tell. And what is that story? That recommendation systems are often not great. In fact, sometimes they're terrible. Maybe even sometimes they redirect the attentive energies of a fair chunk of your civilization in what some might call a negative way. It's a personal opinion. So it seems worth exploring other ways of building these systems. That's what I'll cover in the first section. This will be followed by what I think is an accessible way to understand ML from the ground up. But that is by thinking geometrically. We all have an intuitive understanding of quantity and space, so I'm going to try and see if I can use that to give you all some insight into what's going on with these ML systems under the hood. I'll then move on to the nuts and bolts of our recommendation system, starting with how we built the data pipeline to use news article metadata to construct feature vectors to feed into the dual DQN. I will then go through the DDQN itself, and the overall lesson being that pulling all of these pieces together is challenging, particularly at scale, but that's what makes the work worth doing in my view, and the potential impact of high-quality recommendations on the audience experience is significant. Also, the system is very much a work in progress, but yeah, I'm excited to share where we're at with you today. Let's start with a quote from early internet pioneer Jaron Lanier, who said back in 1995 that, quote, "An agent's model of what you are interested in will be a cartoon model, and you will see a cartoon version of the world through the agent's eyes. It is therefore a self-reinforcing model. This will recreate the lowest common denominator approach to content that plagues TV." Of course, 1995, TV was the big boogeyman affecting cultural and intellectual life and so on. But the point here is that concerns about filter bubbles and feedback loops where users only ever interact with some fraction of possible content have been around for a long time. This is a generalization, but most modern systems optimize for engagement, keeping the user on the site for longer. And these systems are big business. 30% of Amazon's page views are for recommended products. A full 80% of Netflix's views are of recommended content. And of course, YouTube is YouTube because of their system's incredible ability to retain your attention. But what if the incentive schemes were different? What if optimizing for attention was replaced with optimizing for content diversity, finding that fine balance between novelty and relevance, between recommending articles about other natural disasters to someone searching for information on bushfires, rather than articles about how, say, climate patterns have changed over time? Sorry, text didn't switch. The big players are, of course, aware of this, with Netflix themselves explicitly saying that they want to also optimize for, quote, long-term user satisfaction and retention. To do this, they need to understand changing taste patterns and user return behavior, also things our system attempts to do. We can see from my sneaky peek there into their job ads that reinforcement learning is very much part of their roadmap. They've also discussed this explicitly at a workshop at this year's International Conference on Machine Learning. With YouTube, we do know that watch time is a key optimization criteria, thanks to a former engineer who now runs algotransparency.org. They've published as recently as 2016 about their use of deep neural networks to improve recommendations. It's unclear what role reinforcement learning plays in their recommendation systems of 2019, but it seems reasonable to assume that they've at least experimented with this approach. As we'll see, I believe the ABC is uniquely positioned to help develop alternative systems in line with this goal. There are two reasons the organization is unique in terms of the available data we have for building these systems. Firstly, we have daily human-curated recommendations of articles that, in the editorial judgment of our staff, are potentially interesting to the audience. These recommendations are seen by hundreds of thousands of app users monthly. The second is that our news site isn't a pool of user-generated content, like, say, YouTube. All the content is high quality, showing my bias here a little bit, and there is rich topic and subject metadata available for each piece. So the question is, with this unique mix of data, can we do better? Sorry, folks. Let's switch that one manually. Okay, so let's get started with a bit of background into machine learning. I want to try a slightly different approach, particularly following sort of Daryl's excellent talk, in thinking about what is actually going on behind the equations and the code. This is a geometric interpretation of deep learning, and I'm not a mathematician, so I'm going to keep this very brief and practical, and hopefully it'll help you understand the different ML approaches that we'll cover in the next section. So recall the number line we all know and love. Generalize that number line from 1 to 2 dimensions. We now have a flat plane, much like a spreadsheet with x and y coordinates. Add another axis, and we have a 3D space we're all familiar with, now with x, y, and z coordinates. What defines a space? How can we calculate things like distance, the distance between 2 points, or angles to compute cosine similarity and all that good stuff? Well, the mathematicians have figured this all out by defining things like distance metrics and inner products on these spaces. This allows us to perform operations on embedded data points, like, for example, matrix multiplication. These spaces are implicit in the ML systems we build, from the input space to weight space to the loss surfaces that represent how optimized our systems are. Lost the clicker. So this is a bit of eye candy, taken from a paper that used a whole lot of GPU horsepower to produce low-dimensional visualizations of a deep neural network's high-dimensional loss surface. It's often referred to as a loss landscape for a reason. Gradient descent and hill climbing algorithms move along this surface in search of an optimal state, much like those climbing a rocky outcrop might approach finding a peak or valley. Machine learning is traditionally broken down into supervised learning, unsupervised learning, and reinforcement learning. An easy way to think about the differences between them is by looking at the kinds of problems that they're often used to solve and the kinds of data that you can use with each. We all know the cat picture, the canonical example of mapping the cat picture to the label cat, where a system is trained on images and their labels and then will then produce accurate label predictions on new images. So we'll use that as kind of the example as we walk through the different sort of areas of ML. Sorry, folks, just these manual slides are killing me. Okay, so supervised learning first. We can think of our cat image as embedded in that X, Y, and Z space that I very briefly described before, representing the pixel intensity values at each point on our image grid. We can then operate on this input space to induce a feature representation of catness, using the mathematical tools provided by linear algebra to move between input space, feature space, and eventually apply the nonlinear function that produces probabilities, the probabilities of our label cat. Now using our cat example to talk about unsupervised learning, what if we had a bunch of cat pictures embedded in a space that contains representations of other animals too? We might want to identify in our data what is a cat picture and what might be clusters of features representing other animals. Here we can use a clustering algorithm like k-means to distinguish between cat features in our input data as well as those of dogs and goats. The image here is just a low-dimensional representation of what this might look like, where the algorithm labels distinct feature clusters color-coded for ease of understanding. Our dual DQN is an example of reinforcement learning, the third and final area of ML I'll be covering. Instead of learning a function mapping cat.jpg to cat, or identifying catness in the space of all animals, we can think of a cat as a self-directed agent exploring a world in search of tasty mice. When the cat finds a mouse, it learns which steps it took had the greatest contribution to the probability of catching said mouse, building up a memory of these probabilities over time. We can thus define an environment in which the cat moves, and that its moves constitute actions, and the environment has a state that is affected by these actions. Later, we will see how this way of thinking about an agent operating in an environment works in the context of news recommendation. Reinforcement learning had a tangible, memeable result in 2015. Obviously, these systems have been around for a long time. We're all familiar with the deep learning revolution of the last X number of years. So in 2015, DeepMind, now part of Google, sold for a cool $400 million, trained a reinforcement learning system to play Atari games better than humans, using nothing more than the pixel information on the screen and a single scalar reward, the player's score. So I'll play, hopefully this works, I'll play a few seconds of this agent in action. You can see it making mistakes, but learning to slide the paddle around. Let's see if that plays. Learning to slide the paddle around to bump the ball to clear the tiles above, incrementing its score. Some of you, I'm sure, will have seen this before. Okay. So, reinforcement for learning for news recommendations, obviously a very different use case. So now that we've had this 200,000-foot view of machine learning and reinforcement learning, apologies to the data scientists and mathematicians in the audience, how might we use these tools to produce better news recommendations? Earlier this year, I was completing work that used natural language processing techniques to produce keyword and synopsis metadata for pieces of content in our search index, inspired by a nice bump in the click-through rate, and conversion rate of our search users. I was looking at what kinds of other approaches might we employ to enhance discoverability of our content. So I came across this paper, Trawling Archive, as some of us will want to do, a paper out of Microsoft Research Asia that seemed very appropriate for our use case. They used output from an existing recommendation system in an unnamed news organization as input to a DDQN with a focus on novel exploration strategies to reduce the filter bubble problem, ensuring that recommended content was diverse but relevant, that trade-off that I talked about before. It forms the basis for our implementation, and I'll go through the ways in which our implementation differs from the paper when discussing how we process data. So now that we've covered off a bit of ML theory and the background to our work, we can start talking about the system we're building. The first question we might ask regarding implementation of these ideas is, why Go? Firstly, there was no code published with the paper, so we had a clean slate from which to begin our work. The Python data science ecosystem is, of course, in great shape, but for deployment at scale, we didn't want a complex containerized solution where we'd need to jam TensorFlow serving into our existing recommendations pipeline, which includes a custom API and is already written in Go, crucially. Also, quite practically, I've had recent experience building a vanilla DQN for maze solving for a book I co-wrote with the previous speaker, Daryl. This allowed me to spend a chunk of time on the data pipeline itself, which I'll go through shortly. And as always, finding, extracting, and transforming data, the data we needed, was a time-consuming but critical component of the system. And of course, much like our ideal DDQN agent, curiosity. So after working on a number of other projects where I had the luxury of data that was ready to use in the form of large chunks of text as input to language models and images where you map the pixels to tensors, much like in the MNIST example in Daryl's in the previous talk, just getting the interaction log data into a state that we could process it was challenging. The outcome of this is that the data pipeline itself is 71% of the total lines of code for this project. At this point, I should give a big shout out and thanks to my colleague Lapang Ho in the ABC's data science team. He has a deep understanding of our data and has been exceedingly generous with his time through the duration of this project. So there were two parts to data processing. First, we had to pull completely anonymized data from the news app for the module providing users with recommendations. For those of you who have the app, this is the various set of links in the top stories section sort of as you open the app, and this is a human curated list. So this is where we kind of differ from the paper in terms of the data that we fed our system. So we then joined this up with link referrer data, which told us which of these top stories the users clicked on and represented each interaction as a single row with different columns for metadata. And this is what the data actually looks like, the structure of the data anyway. This is dummy data that we used for initial development. There's not real user IDs. For the real data, we first pulled this data manually from our data warehouse, and after getting the query right, we then used the excellent PQ library to connect to the database and pull the data directly. This integration was important for online processing, by which I mean pulling new or very recent interaction data to update the weights, to use with the experience replay function, and update the weights of our DDQN dynamically. So what happens to this interaction log now that it has become a slice of the struct shown in the previous slide? Our system calls for a number of feature vectors representing different aspects of our users and the news that they consume. The term vector has a specific meaning in math and physics and computer science, but because we're highly practical engineers at a Go conference, for our purposes, it means a slice of integers. Specifically, we carve our data up into 4 vector types. User features, so for each news candidate or URL, a slice that represents whether or not a given subject appears in the article metadata. And I'll go through all of these in detail next. We also have user features, so for each user, a slice representing a history of subjects they've interacted with at periods of 1 hour, 6 hours, 24 hours, 1 week, and 1 year. So a distribution of subjects over time. Context features as well, for each interaction, a slice representing the context, i.e. the timestamp of an event. And then we finally have user news features, which for a given user, a slice containing counts of all subject interactions, so a historical summary, rather than capturing changing tastes over time, as with the user vector itself. We're also concerned with vector sparsity, which is a measure of how much information we're really feeding into our DDQN. And this is just simply the percentage of entries of our feature vector that actually contain values. As a rough guide, we want to be between 1% and 2%. So I'll now describe how we generated each of these in turn. So news vectors first. The challenge with news features was capturing as much information about the subject metadata of a given article without producing low information vectors. We did a bunch of work outside of the pipeline to determine how many possible subjects existed across all ABC News articles. The number was 1,380, translating to an average sparsity of 0.38%. This was too low. So we began to cull subjects that were associated with less than n articles. Our current threshold is 100, leaving us with a vector that has 590 elements and an average sparsity of 1.11%, serviceable for now. We include additional features like whether the article has a large number of keywords, whether the article is lengthy, so if it has a read time greater than n, and which part of the ABC the article comes from. As you can see there, sort of in the indices, and then sort of as the concatenation of the vectors. So yeah, as I said, they're concatenated together to produce a single feature vector, and of course is long read time and is many keywords are tunable, both tunable parameters up front. So as we've seen in the example of the raw data, we also need to obtain metadata for each of the URLs in our list. The basic idea with user features is that we want to capture changing tastes and user preferences regarding the types of content the user is interested in at different time intervals. To do this, we loop through all the URLs the user has clicked on and populate a temporary vector for each interval with values if the click is within the range we're interested in. We then update the existing values of the main vector only if those values are currently 0, i.e. we update only if the content the user has clicked on is indeed new to them, within the time interval specified, of course. As you can see from the code snippet, this is hardly rocket science, just a bit of legwork and lots of testing, because you don't want bad data. So, moving on to user news features now. The user news features are similar to the user features themselves. Indeed, we generate them inside the same loop. However, instead of tracking user preferences over time, we want a historical summary of the level of engagement with certain subjects. This means instead of a long vector of zeros and ones, we have a relatively short vector of length 590, so what would be one time interval, in contrast to the user vector, and with the totals of each, as you can see in the example up there. So the context features, our final feature set, is they differ slightly in that we're not producing a map indexed by user ID or URL, but rather a slice of features for each time step or user interaction. The features we're producing are a simple representation of when the click occurred, as you can see by the snippet showing the vector's index. Like I said, not rocket science. We augment this vector with a freshness metric, which sets the corresponding element to 1 if the tunable freshness criteria is met. Say, was the article published in the last n hours? So now that we've processed our interaction log and generated all these features, what does this mean for our DDQN? Recall from our slide on reinforcement learning and the Atari game example, we have our environment, which in the case of news recommendations is our user news candidate pool. Our state becomes a concatenation of the user and feature vector, user and context feature vectors, and our action becomes a concatenation of the user news and context feature vectors. Now that we have our data and understand what maps to what in the context of reinforcement learning, let's see our data pipeline in action. So here's the, good, that's quite visible from a distance. Here's what the offline component of our data pipeline looks like. In this output, we're ingesting 3.7 million interactions with that top stories module in our news app over a period of 6 months for a sample of 10,000 users. So you can see there an example of what the struct on the right contains. Just the timestamp, the anonymized user ID, blanked out here for the purposes of irrational completeness, and a list of contents and click values. On this slide, we can see that article metadata is loaded locally. That's actually a dump. This file referred to up there, that's ABC productional JSON, is actually a dump of our entire search index, which contains every sort of piece of metadata we might be interested in about a given piece of ABC content, like the subjects, the read time, the keyword metadata I talked about previously. This is an example of one of those bit of work in dev type problems that seems obvious in retrospect. Our initial work was done on a small sample of data, so for each unique or new piece of content, we would hit our search API and retrieve the metadata when generating that news feature vector. But of course, this is highly impractical for processing millions of interactions with hundreds of thousands of articles. So I pulled the metadata down locally as a giant blob of JSON, and then I loop through this blob and extract per article metadata indexed by content ID. The pipeline then produces the feature vectors we've just talked about and writes them to a number of JSON files for offline processing by DDQN. Here I'm showing just a few snippets of the DDQN. We'd love to open source parts of our project at some point, but first we need to mature the project and ensure that any code we release into the wild is done so responsibly. We're using Gorgonia and the upcoming Keras-like interface called Golgi that Daryl talked about previously. And that actually reminds me, Daryl did ask me to mention that he will be releasing his code on GitHub, so please follow him on Twitter to check out that link when it's available. To create our DQN. So it is comprised, this DQN, of 2 simple feed-forward neural networks, so the most basic kind of neural network, that collectively produce our queue function. As we're building and then executing a graph, we define a number of nodes relating to our inputs, predictions, Q-table, and cost function. We also define a number of hyperparameters that relate to how our agent explores this environment. And a key part of the system that's used for online training, so as distinct from the offline training example I showed you just previously, key part of the online training phase of the system is this episodic memory struct. So that when the system is deployed live, it retains a memory of recent states, actions, and rewards, and it uses this to update the weights of our network at regular intervals. You can also see a simple representation of our states. Recall that this is comprised of our user and context feature vectors. I've also included the predict function, in which we get a dense tensor representation of a sample input, put it through our graphs VM, and produce a prediction, in this case the index of a piece of news content. So this graphic is taken from the original dual DQN paper by De Freitas et al. At Google, released in 2016. The vanilla DQN is on top, and the DDQN is on the bottom. So in the first half of each graphic, the boxes containing the bits of blue, that's representing the process of feature extraction by a convolutional neural network, not relevant necessarily today. But we can see that the final step, the red vectors, that's where the action is. In the case of the DDQN, we split the Q value function in two. We end up with an advantage function that takes both state and action vectors, and a value function that takes only a state vector. This image captures exactly how that Q function is split. We can see how the concatenations of our different vectors, the ones that I've talked about previously, feature vectors end up in one of the two neural networks, collectively producing the Q function. What is the purpose of splitting up the Q function, you ask? The answer is efficiency. We need to calculate the value of each action at a given state. But if the state does not affect the environment in a way that is relevant to the agent, all that computation is wasted. So we decouple them and learn the value of a given state independent of actions. So now we come to a conclusion, hopefully the beginning of an answer to why build all this stuff. Here, we end up with a system that uses a novel exploration strategy for exploring the space of possible content for a given user based on a history of their preferences and changing tastes. We also have a single dial for controlling the cosine similarity of these feature vector representations of news content. This is a departure from the systems we have and a step towards a future where we have control over precisely what we optimize for, backed by criteria that are not purely about keeping the audience's eyeballs on their screens. The paper our work is based on was able to deploy their system in a live environment, capturing user behavior in response to the system's recommendations to improve that performance. Our compact with our audience prevents us from doing this. The ABC's editorial policies are strong for a reason, and we only want to present recommendations to our audience that we have confidence in, not use their live preferences to train our system. This means building a simulator that takes offline data and makes predictions about whether a given user will pick a prediction from our DDQN. Yes, it's predictions and probability all the way down, folks, and that this is really the current focus of our work. So what else is next? As I've described, there are many, many improvements we need to make to the system to ensure its robustness before deploying it to an audience-facing product like our website or the news app. We also aim to introduce new information into the system to avoid feedback loops. This information takes the form of successful searches, where the user has indicated a novel content preference outside the content recommended to them. Another area of improvements is the range of features we capture about a given news article, using the kind of textual features that show up in language models used for text generation and translation. Performance evaluation and filtering are also a big component of the system. Our current recommendations platform includes options for filtering content based on content types and keywords, and this work will be a module in that system, ensuring continued familiar ease of use for content teams integrating recommendations into their apps. And finally, the ABC's new managing director, David Anderson, has the mandate to, quote, engage new audiences online and create a personalized and connected online network. Personalization is very much a priority for us, and we aim to do this in a responsible, ethical way, ensuring that the ABC remains the most trusted media organization in Australia. That's it. Thank you. Thank you.